Hey folks, this is Miss Gray. Welcome to your fall break assignment, Organic Chemistry. We're going to talk first about how to name organic compounds. There's a system to this, and you'll have to learn the basic rules, and when there's exceptions to the rules, I'm going to tell you about it. So let's go ahead and get started. First of all, we're going to start with the straight chain hydrocarbons. These are the backbone of your organic molecules, so knowing how to name these is pretty important. Methane is the name of our first carbon group. Methane is basically one single carbon and then enough hydrogens to fill in a bond for each carbon, or for each electron. Remember, carbon can form 4 bonds, and it must form 4 bonds so that it can have a complete octet. And so every time we look at organic molecule, carbon has got to have 4 bonds, and it's not allowed to have more than 4 bonds. All right, what's next? The next one would be ethane. Ethane is the 2-carbon backbone. So we have C2H, what should that be? What's it going to take to have 2 carbons with complete octets? Well, if the 2 carbons bond to each other, then that leaves room for 6 other hydrogens to be there. So ethane is going to be C2H6. That's ethane. So I guess you can figure out the pattern here. Propane is going to be 3 carbons. So if I have 3 carbons, then how many hydrogens can I attach here to get every carbon up to 4 bonds? Well, that one's going to have 1, 2, here 1, 2, 3, 4, 5, 6, 7, 8. So C3H8. For all of these are called alkanes. Single bonded hydrocarbons, all ending with ANE, alkanes. So the next one, butane, is going to be our C4. After this, it's going to be pretty simple because we use the Greek prefixes that you're already accustomed to. But up to 4, they all have had special names for so long that chemists just kept the names they've always had: methane, ethane, propane, and butane. So these are your alkanes. Then after this, we're going to use prefixes. Pentane is for the 5-carbon chain, C5H12, and then hexane is C6H14. Heptane is C7H16, and then octane C8H18, and on we would go, nonane and decane and so on. Notice, though, there's a pattern to this. Every time we have some number of carbons, the hydrogens will always be twice the number of carbons plus then the 2 on the ends. So we call it 2n plus 2. So no matter what you're given here for carbons, you'll always be able to figure out how many hydrogens you need to completely fill it in, 2n plus 2. Now we use these as the backbone of our organic molecules, but we also use them as groups to attach to other hydrocarbons. When we do, we change the ending of their name to YL. As if it was an adverb, we'd call it LY, like if you were going to be quick about something, we would call it quickly. Well, now, if we're going to put a methane somewhere, we're going to call it a methyl. So it's kind of like an adverb, only a flip-flop. Methyl, ethyl, propyl, butyl, and so on. So those are the prefixes that we'll be attaching to things to indicate that there's a group that's derived from methane attached to it. So let's modify the straight chain. There's 2 ways we could modify. We could make double bonds, or we could make triple bonds. A double bond would change the ending of our hydrocarbon from ane to ene. And so that would be like with ethane that has 2 carbons. We put a double bond between the 2 and it becomes ethene. And then of course we've got to make sure every carbon has 4 bonds. So I need 2 more here and 2 more here. We'll just fill in the hydrogens so that the chemical formula for ethene is C2H4. There's ethene. We would also specify the location of the bond using a number. With ethene, there's only one place where the double bond can go. But suppose we had something bigger than ethene, like, let's use butane. There's butane. And with butane, I can put a double bond here, or I can put a double bond here. So I would need to distinguish between these two. Of course, there's hydrogens everywhere. It's pretty common to just show the carbon backbone and not the hydrogens. So in this case, I have the bond on the first carbon. In this case, I have the bond on the second carbon. So we count the carbons to get the lowest number in the name. So what I have here is 1 butene. And then down here I would have 2 butene to indicate where that double bond is taking place in the molecule. Normally, though, if it's in the first position on the first carbon, then we don't call it 1 butene. We call that normal butene. So it's pretty common to see it written as N-butene for normal butene, meaning the double bond is just on the terminal carbon. Remember, too, that when we're looking at bonds, these are three-dimensional molecules, and so this particular structure is exactly the same as a structure like this, because we're always going to count in such a way to get the lowest number in the name. So if we count 1, 2, 3, 4, then this would be N-butene, or 1 butene. And here, if we counted 1, 2, 3, 4, then we would get 3 butene. But that wouldn't give us the lowest numbering. So we would start counting here, 1, 2, 3, 4. So we still have 1 butene, or normal butene. Always count your carbons to get you to the lowest number in the name. And even if it's crooked, it's still the same. That's still 4 carbons. Even if I hang one down, it's still 4 carbons, because it's still all in a row and we don't have any branches coming off. So that's still butane. Whoops, I forgot to go back to triple bonds. With triple bonds, it's a similar situation. Basically, instead of having a single bond, where we would have ethane, we'd have a triple bond, and then this would be called ethyne. We're going to change the ending of the name to show that now we have a triple bond. So we change it to Y-N-E, and it's pronounced ine. If we need to, we'll specify the location of the bond using a number. So if we have a triple bond, then this would be propyne. There's only one place to show a triple bond in propyne, because if I drew it this way, then I would just count backwards. Instead of going 1, 2, 3, I would go 1, 2, 3 in the other direction, and it would still be normal propyne no matter where I put it. Of course, with butane, I would have to specify so that I could show a difference between normal butane, and then of course we can have 2-butane that would look like this. So use the numbering system to indicate where that bond is located, and then we just name the backbone using methane, ethane, propane, or butane, and of course other prefixes as necessary. Now let's look at some more complicated ways of showing these carbons. This is one way of writing a formula that indicates where all of the hydrogens are. So this shows that our double bond is right here, and then I have a methyl group with 3 hydrogens, and then this would have a hydrogen, and this one would have a hydrogen, and then over here I have an ethyl group, right? 2 more carbons. So that has 2 hydrogens stuck to it, and then that one is on the end, so it would have 3. So let's count so that we get the lowest number. 1, 2, 3, 4, 5 carbons in this chain, so it's going to be some kind of pentane. But since we have a double bond, I'm going to change the ending to ene, pentene. Now let's use a number to indicate where the double bond is located. So we call this 2-pentene. All right, now the next one is N-propene, normal propene, so we put the double bond right there in the middle. That one was pretty simple. There's only one place for it to go, right? How about 3-octene? Octo means I need 8 carbons, right? 1, 2, 3, 4, 5, 6, 7, 8. Where are we going to put the double bond? On the third one, right there. Now, of course, we might want to show where all the hydrogens are, so we could write the formula. So let's see, 1, 2, 3, 4 bonds, then 1, 2, 3, 4 bonds, 1, 2, 3. So how many total hydrogens do I have? 1, 2, 3, 4, 5, 6. C3H6 is one way to write that formula, but it would be more descriptive to show that I have CH2 bonded to CH bonded to CH3. This is an indication, because of the way I've written these, that there's a double bond. If all you have is this, it doesn't give you much clue about what type of isomer you're dealing with. C3H6 could come in lots of different forms. If I write it this way, then it's pretty clear to anybody who's looking that the only way you could have a CH2 and a CH3 stuck together and every carbon be happy is to make a double bond between the two carbons. Alright, so here's our octene. How would we write this one? I'd have to have 3 hydrogens here to make this carbon have 4 bonds, and then 2 here, and then I can only put 1 here because I have 1, 2, 3, 4 bonds on this carbon. Then 1, 2, 3 already. There's my 4th one. Now let's put 2 more. 2, 2, and then on the end we got to have 3 so that carbon can have 4 bonds too. So what do we have here? We could write it this way, where we have CH3, then CH2, CH, CH, CH2, CH2, and I'm running off the screen. Let me put a new color so you can still read it. Let's see, CH2, CH2, another CH2, right? Yep, 3 of them, and then a CH3 on the end. Wow, ran out of space there. So that would be a really long and cumbersome way of writing 3-octene. Usually, it's not written that way, but at least it shows that the double bond is in here. Oops, here. Yeah. We got it. Alright, then 1,3-butadiene. What is this? So I have 2 numbers, which means I have 2 double bonds, thus the word diene. So buta means 4. 1, 2, 3, 4. And then I have a double bond on the first and a double bond on the third. So there is 1,3-butadiene. Every carbon needs to make 4 bonds. So let's make everybody happy. So the overall formula is C4, and then how many hydrogens? 1, 2, 3, 4, 5, 6. C4H6 to make 1,3-butadiene. So the double bonded hydrocarbons can get a little complicated, but name your backbone, number your carbons, and you'll be fine. Here's some triple bonds. A triple bonded carbon could be N-butyne. So let's start with our butane. There we are. And then we have N, which tells me it's the normal kind, so I'll just put it right on the front. So this carbon needs to have a hydrogen here so that it can have 4 bonds. This carbon right here already has 4 bonds, 3 with this carbon and 1 with this carbon, so we cannot put any more hydrogens there. Then I need 4 bonds for this guy and 4 bonds for this guy. Let's write this formula. C4, and then how many H's? 1, 2, 3, 4, 5, 6. Hey, the same as 1,3-butadiene. So that's why we need to know the molecular structures to be able to distinguish between these. Here's another one. We have a triple bond between 2 carbons and then a CH3 on the end. So we would call this propane normally, right? But since it's got a triple bond, we call it propyne. I don't have to call it 1-propyne. I could call it N-propyne. That would not be inappropriate. It would simply be redundant because if I, oops, I need my triple bond to triple. If I put my triple bond in here, I would just start counting backwards and get the lowest number, right? Now let's do 3-heptyne. Hepta is 7. 2, 3, 4, 5, 6, 7 carbons. And I need my triple bond on the third one. So there it is. There's 3-heptyne. To write this chemical formula, I know I need 7 carbons, 7 carbons. And then this carbon needs 4 bonds. This guy needs 4 bonds. This carbon already has 4 bonds, and so does this guy because they are in a triple bond, right? Then make this one happy. 4 bonds on every carbon to fill it up. So now let's count. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens in that formula. So there's my chemical formula that doesn't give much information about the molecular structure. It's simply telling me the lowest whole number ratio of atoms in this compound. Sometimes we have branching hydrocarbons. Branching hydrocarbons simply means that there's something attached to the backbone. So we name the longest chain as the backbone, and then identify the branches by the number of carbons they contain. We call them methyls or ethyls or whatever. We'll locate where the branch is by using the numbers on the backbone again to get the lowest number of carbons. And then if you have multiple branches, we list them in alphabetical order. Seems like I'm missing something. We're going to also look at something called iso and tert. But first, I'm going to draw a few of these so that we get the hang of this. All right, so let's take a propyl. Here's my propane, and I'm going to hang a single carbon off the middle. All right, so this is called methyl propane because I put an extra carbon on my propane backbone. So I count my longest chain. This 3-carbon chain is longer than this 2-carbon chain, right? So I name my longest chain propane, and then I have my methyl group, this single carbon hanging off of the propane. There's only one place I can put it, because if I put it on the end, then I turn my propane into butane, because now I have 4 in a row. Alright, so butane and methyl propane are different because my carbon is attached to a different spot. Then I need to fill in my hydrogens so that everybody's got 4 bonds. Alright, so methyl propane is going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 C4H10, which is the same formula as butane, C4H10. But because the carbon is in a different place, it has a different name, and it also has different chemical properties and different physical properties. Different boiling point, different melting point, but it's the same exact molar mass. So where the carbon's located makes a big difference, and we want to make sure we get this right. Now's a good time to talk about this word iso and tert. Because butane is closely related to methyl propane, then there's another old-fashioned way of naming this. This is called isobutane. If we attach something to the central carbon in this shape, then we give it this prefix iso. And then sometimes we have sort of a crisscross thing. That's what makes it something called tert. So I could have something like this, where now I have 5 carbons all arranged in a circle around this central guy. So this is called a tert pentyl, because I have 5 carbons, but they're in sort of a cross. So they're all attached to that same central thing. That's kind of the old-fashioned way of naming this. we could have isooctane, which is the compound that they use for octane ratings in your gasoline. You know, the 85% octane or whatever. It's isooctane. But its scientific name is trimethylpentane. So let's draw our pentane. So we need 5 carbons, and it's 2,2,4. So that means I have 2 methyls on the second carbon. Then on the 4th carbon, I have 1 more methyl group. So that means every carbon's got to have 4 bonds, right? So we'll fill in our hydrogens so that everybody gets to have 4 bonds. So that makes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 carbons. So we get C8H18, just like octane. Thus the term isooctane, because everything's arranged in sort of this whole crisscross thing. But the scientific name that helps you know exactly where they're attached is 2,2,4-trimethylpentane. That's the naming system we're going to use. It's called the IUPAC naming system because it's the way scientists around the world have agreed to name things. Now let's look at a couple other branched hydrocarbons. We could start counting from this end, 1, 2, 3, but if we do, then we're going to get too high of a number here. So I have 5 carbons in my main longest chain. I want to start counting though so that I get the smaller numbers. So rather than going from left to right, I'm going to go from right to left in my counting so that I can call this, let's see, it will be 2-methylpentane. So put a dash between a number and a letter, and then don't use a space for your prefix, methylpentane. 2-methylpentane tells us the location of this group on our pentane molecule. Now let's look at this one, because these two don't quite look the same. Let's see, 1, 2, 3, 4. Nope, not quite the same. So we'll call this guy 2-methyl, what? What's the 4 carbon? 2-methylbutane. You got it. All right, now I've got 2 different groups here. So I have a 1 carbon and a 2 carbon, and then 1, 2, 3, 4. So my 4 carbon is my backbone. Let's name it butane because that's what we use for 4 carbons. And now we're going to identify where the substituents are. So I need to go in alphabetical order. Ethane or ethyl comes before methyl in the alphabet, so I'm going to name the ethyl first. So I need more room to write. We're going to have to call this 3-ethyl. I need a hyphen. 3-ethyl, comma, 2-methylbutane. So here's my backbone, 4 carbons. The methyl group is attached to the second of my 4 carbons, and the ethyl group is attached to the third of my 4 carbons. That's how we name a branched hydrocarbon. All right, let's look at this one. 1, 2, 3, 4, 5 carbons in this chain. If we went this way, I would have 3 carbons in a row. So 5 carbons wins, right? So pentane is our backbone, and my 2 carbon chunk is attached to my 3rd carbon on my backbone. So it's going to be 3-ethyl pentane. That's it. Name your longest chain as your backbone, and then name whatever's hanging off of the backbone and tell me what its name is. All right, I need more room to write again. So here looks like my longest chain, 1, 2, 3, 4, 5, another pentane, and I have a methyl group here, and a methyl group here. So we'll call this 2,4 dash dimethyl, because I have two of those guys, so dimethyl pentane. And that's it. We can handle that, yeah? You're going to get lots of chances to practice this, don't worry. Oh, let it spin. Here we go. There's another type of crazy hydrocarbon. It's called a cyclic hydrocarbons, where now we're going to take it and wrap it around itself. We use the prefix cyclo to indicate that it's going in a circle. We name the hydrocarbon based on how many carbons there are, and then we would use counting for anything that's branching off of our cyclical hydrocarbon. So let's start with cyclopentene. Penta is 5, so I would take my 5 carbons. There they are. And then this ends with ene, so I've got to have a double bond there. Now I need to wrap this around so that this carbon is bonding to this carbon. So I'm going to make the tail come back to the head. Here we go. Double bond, single, 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 single. If I had 2 double bonds, I would call it cyclopentadiene. But I don't have 2. I have only 1, so it's cyclopentene, just like that. It's pretty common when we're making molecular structures to not write the carbons in. So instead of putting a carbon at each corner, it's just implied. There's a carbon at every corner in this shape. So count up how many corners we have, and we know what kind of hydrocarbon this is. This is our 6-sided shape. We'd call it a hexagon, right? Well, this is hexane, only this is hexane in a circle, so we call it cyclohexane. And then this guy has got 4 corners. Each carbon is at one of these corners. So a 4-carbon compound is called butane, only this guy is put in a circle, so we call this one cyclobutane. That's it. Cyclic hydrocarbons are pretty simple to work with. But there's a special one that you need to know about. Its name is benzene. This cycloalkene is a particularly stable structure, so it shows up a lot in nature, like a lot. We have 6 carbons, and they have alternating double and single bonds. So rather than having our regular cyclohexane, what happens is that the carbon forms a double bond and a single bond, then a double bond and a single and a double and a single. But who's to say that the double bond belongs here? Why couldn't we put it here? Well, if we did, then it would look like this. We'd have the double bond in this spot, and then in this spot, and then in this spot. So what truly happens is that the double bond tends to sort of meander. It's on all of them, not just on one of them. But because it can't be on all of them at the same time, then each bond, rather than being truly a single bond or a double bond, tends to be 1.5 bonds because it moves around. And so it's drawn this way with this circle to indicate that the double bond is transitioning from one location to the next all the way around the molecule, and every bond has, instead of a single or a double bond, it really has 1.5 bond order. So we call this one benzene. Benzene. There we go. And the structure of benzene was not really that easy to figure out for scientists. They were confused for a long time. But benzene shows up in many, many organic compounds. It's not easily water soluble because this symmetry in the molecule prevents it from being broken apart by water into any sort of ions. So what if we have branches hanging off of our benzene? No big deal. We start numbering and then we use our prefixes. So this would be called 1,2-dimethylbenzene. So that's its scientific name. There's a common name for this that organic chemists are probably familiar with, but all you need to know is how to put the prefixes on, and that this hexagon with the circle is called benzene.